So as part of the electrochemistry unit, we're going to be talking about two types of electrochemical cells. And the first one, which is the one that tends to be much more common on the AP exam, is called the voltaic cell, also known as a galvanic cell. And a galvanic cell is one that is thermodynamically favorable. It means it will happen without any type of assistance, whereas the electrolytic cell, the other type of electrochemical cell, is thermodynamically unfavorable, which means it needs an external source of energy to get the reaction going. So what we want to talk about with this is that what you have is you have two separate, we call these containers, of one is called the anode and the other is called the cathode. Okay, and this container has a zinc electrode that is immersed in a solution of zinc and nitrate ion. And this is the copper electrode, which is immersed in a solution of copper 2+ ions and nitrate ion. So the overall reaction for this is, I'm going to have you write this down, is zinc, solid, plus Cu2 plus aqueous gives you Zn2 plus aqueous, and Cu solid. And there's a change in oxidation numbers which indicates that this is a redox reaction. And in general chemistry, honors chemistry, whatever you took beforehand, you could have the situation where you mix all of these together. You have a solution of, say, zinc that's immersed in copper 2 nitrate in a single replacement reaction, and the zinc becomes Zn2 plus ion, while the copper 2 plus collects on the zinc electrode, the zinc metal. Okay, but what we do is we separate these into two half containers, and we connect them with a wire, and that wire passes through what you call a voltmeter, which measures the potential, the electric potential difference between the two metals, between, in this case, the zinc anode and the copper cathode. And in a later lecture, we'll be talking more about what that potential difference is, but you should note that a voltmeter measures that potential difference. And again, we'll talk about what the implications of what that voltage will tell you about the thermodynamic favorability of the reaction. So what's happening here is you see the two half reaction. One of them is the oxidation of zinc, that's listed right here. And I'm going to go ahead and highlight that below so we can draw our attention to it. And then you also have on the other side the reduction equation right over here. So if you remember, oxidation is losing electron. So what's happening in this process is that the electrons are traveling from the zinc metal, through the wire and going to the copper. So what's happening here is literally you have electron traveling along the path of this wire, and that, my friends, is where you get electricity. When you have the flow of electrons moving through, that generates that electrical current. So because this is a thermodynamically favorable process, this means that with this apparatus, if you connected a wire between the zinc metal and the copper metal, the electron would be generating that electrical current, and that would be happening without any external assistance. Now, in an electrolytic cell, the electrons would be going backwards from here all the way to the zinc, and in order for have that happen, you have to add a power source because that reaction would not be thermodynamically favorable. Okay, so that's the general gist of how the electrochemical cell operates. So I'm going to go ahead and have you move to the diagram below in your lecture notes. That's the same. I'm talking about another aspect of the electrochemical cell. So the next thing I want to draw your attention to is what you call the salt bridge, which I'm going to highlight this right here. Okay, so let's note that this is called the salt bridge. And it is composed of inert electrolytes. I think oftentimes it's going to be a combination of K plus ion and NO3 minus ion here. And a salt bridge is necessary to get the electrochemical cell to operate, because if you think about this, as the reaction proceeds, as the zinc is losing electron, you're going to get a buildup of the Zn2 plus charge. So you're going to get a buildup of positive charge here. And then as the electrons are moving to the copper cathode over here, the Cu2 plus will then be reduced to Cu solid. And as those get removed from the solution, this goes down right here. This decreases, and you end up getting a buildup of a negative charge. So when you have a charge buildup, the galvanic cell will no longer operate, and so that's where the salt bridge comes into play. And what the salt bridge does is that it helps to maintain the electrical neutrality of each of these half cells. So as there is a buildup of a positive charge over here, the NO3 minus in the salt bridge will then become attracted, and the salt bridge will keep depositing nitrate ions in here to neutralize the excess Zn2 plus ion to allow the electrical current to pass through. Okay. On the other side, as you get a buildup of a negative charge, that's going to attract the positive ion, which is, I said, either potassium ion, but sodium ion could also be a good substitute. And those positive cations will then be attracted into this part of the half reaction, and once again help to maintain the electrical neutrality. If the salt bridge was removed, if you take it out of the two solution, the reaction would cease to operate and the cell will no longer be functional. So it is very important that we have that salt bridge in there to help maintain the electrical neutrality. Okay. Moving on, let's go ahead and go to that final diagram. Again, that's the same thing. And this time I wanted to bring your attention to what you call the anode, which is right here, and the cathode. Okay, and I think it's helpful to remember the vowels. Oxidation occurs at the anode. Okay, so you can see the vowels O and then the A. And meanwhile, reduction, okay, occurs at the cathode. Okay, and then you see the consonant in this case. So the zinc is the anode, so that's where the oxidation is happening as the zinc atoms are being oxidized to Zn2 plus, and copper 2 is being reduced to Cu. Okay, so you can see how the electrons, and I don't want you to memorize this per se, but if you think about it, because they're losing electrons at the anode, that means that the electron flow is going from the anode to the cathode. Okay. So what does this mean, how the cell is going to look? Because the Zn is going to Zn2 plus, you have a solid that is going into aqueous state. That means that the mass of the anode will decrease over the course of the reaction. And at the cathode, because you have the aqueous ions in here turning into Cu solid, that means the mass of the cathode will increase. And we're going to be doing a simulation in class very soon, where I think this illustrates very beautifully how the mass of the cathode will increase and the mass of the anode will decrease. Okay, but I think hopefully that gives you a pretty good background into how the electrochemical cell operates, specifically a galvanic cell. And throughout this class, I'll probably be referring to the galvanic cell commonly as opposed to voltaic cell, but note that those two terms are interchangeable. Okay, all right, that's it for this part of the lecture.